All right, which ones do I look at? I want to look at those graphs for sure where you had to compress and stretch. You know, one of the quiz on Thursday, right? Quiz on Thursday. A lot of stuff from this section in there. I mean all the sections, but even odd, periodic, the shifting, compressing, that kind of thing. Either being able to do it with a picture or graph it, like somebody had some really good pictures. You really needed to have, if you got graph paper, which isn't a bad idea, but on your pictures, you really need to have some points, either labeled or some marks, so you know, okay, where did this point go? It went up, it went in, it compressed, it stretched, whatever, okay? And so be particular about that. Now, if I had to do it on the quiz, I'd probably have some grid there to help you to draw that, you know, be more exacting about it. But you might also just have to explain, right? Write out in words what's happening. The word stretch and compress by a factor of this or shift up to or whatever. So be able to do that as well. So that's important. The even, odd, periodic stuff's important, those kind of things. So what, well, we were talking this morning. There was a few people in, and we were talking about even these early ones, like 2 and 4. And so let me just talk about that a minute. You know, because I mentioned this earlier last week, like on number 2, it says that the function b crosses the x-axis at negative pi, and it crosses the y-axis at 3. Okay, and so what that tells you is there are points there. Now, we don't know what the rest of the graph does. I mean, who knows? I mean, it might come down like this, and then go here, and then come back, and then come down. I mean, I don't know. Who knows what that does? But we do know those 2 points. So then they ask, the very next question is, what's b of 0? Evaluate, which means find the value, evaluate b of 0. Well, what are they saying? When you have a function and they say find b of 0, what are they telling you to do? Find the y value when x is 0, right? Plug in is what a lot of people say. Now, to plug into an equation is one thing, and that's what we're used to doing, but we got to get used to graphs. And so it says b of 0, that means plug in a 0. That means go to the x-axis at 0 and see the y value. Oh, it's right there, it's 3. Okay, what's b of negative pi? That means plug in a negative pi. On a graph, to plug in means go to the x at negative pi and get the y value. Oh, the y value right there is 0. So that was, so maybe you did those yesterday in class and didn't think a thing of it, thought, boy, that's really easy, and that's good, because that means the language of functions you're good with, and you need to be, because that's how we talk all through calculus, is in the language of functions. So that's what was going on. Remember, I said that we're not going to talk here in this class, we're not going to call that point 0,3 very often. What we're going to say is we're going to say that. That's how we say the point 0,3, okay, on a function. And then the same thing is true, the same thing is true on number 4. It says, kind of the reverse. It says f of 0 is negative 2. Now, when I see that, not depending on the problem, but when I see that, almost always I go and draw and plot that point. Because when I see that, I'm saying to myself, they're telling me a point. They're telling me a point on the big F graph. So I'm going to go and I'm going to plug it in and plot it. Okay? And they tell me that f of 2 is 0. So that tells me that I got a point right there. Okay? So then they say, is there a root at x equals 0? Well, that'd be right here. No, there's not. Is there a root at 2? Yeah, that's what that is. A root means it crosses the x-axis. Okay. So those are some questions that we were talking about with some people this morning, so I just wanted to clarify that in case anybody had questions there. Okay, what else? Anything before question 35? Anybody got one? 21 and 23. So, okay, this is that one with the period. Yes, and this is, I talked about this yesterday. This could definitely be a question on the quiz. The period, the function is t. The period is 7. And so they tell you that t of 0 is 3. Now, maybe you could do this graphically. We didn't yesterday. But since I just got done saying that if I'm given this, I plot it, so maybe that's a good thing to do. So maybe a good thing to do would be to say, okay, I'm going to go to the t function, and I'm going to plot that point. Okay, so 0, 3. All right? And if the period is 7, what's that mean? That means every 7 units, I'm going to repeat that point. That's what that means. And so back here, 7 units, I'm going to repeat that point. I don't know what's going on in between. I have no idea, but I'm going to repeat those points. And so now I don't have room, but what does that mean? That means T of 7 is 3. And if I kept going, T of 14 would be 3, right? And so that's 21. 21 is T of 7, so T of 7 would be 3. And if I keep going this way, so T of negative 7 is 3, and I keep going to the left, T of negative 14 would be 3. So that's 22. 23, okay, so here's a different way of asking this. So T of negative 30 and T of 40, well, if I keep going, 7, 14, 21, 28, 35, 42, oh, I'm not going to land. So I don't have any idea what T of 40 is, right? I have no idea what T of 40 is. So how in the world can I answer that question? Anybody, any ideas?
T of 40 and T of negative 30 are 70 away.
Okay.
Also, T divided 7 by 7 again.
Okay, so I don't know what this value is right here at negative 3. I don't know what that y value is. But I know that if I go 1, 2, 3, 4, 5, 6, 7 away, which would be here at 4, I know those two have to have the same y value, right? This, whatever this y value is, I don't know what it is, it's got to have the same y value as 7 away. And so T of negative 30 and T of 40 are 70 apart, right? From negative 30 to 40. So that's 10 periods. They have to have the same y value. And remember what we said is when you see this, you think y value. You think output, right? So this is a y value, this is a y value. They're 70 apart on the x-axis, so therefore they have to be. Okay? That was 23. Did we do 24? Was 24 one we did? No. Okay. But if we were, it says let S be T of V plus 21. Well, what does V plus 21 mean? Left, 3 periods, right? So if you take a graph, pick it up and move it over 3 periods and set it down, it doesn't land right on top of itself. It's be like the sine curve, right? You take the sine curve, pick it up, move it over 2 pi, it's going to land right on top of itself, be an exact copy. So what they're saying is that S and V are the same. S and T would be the same direction. Because if you take the T graph, pick it up, move it 3 periods over and set it down, it's going to be an exact copy of itself. And so S, because all those values are going to be the same when you move over. Okay? So just another way of asking. All right. What else? Anything else before number 35? Answer books are up here if you want to ask later. Okay, so let's go to one of these. Okay, so 35, pretty simple, just going to shift up 1. 36, just going to shift left 1. The one that we sometimes struggle with, well, actually, this is 37 is the one I did in class, wasn't it, yesterday? G of 2x is going to just compress everything in by a factor of 2. So it's just going to go in. This is a 5. It's going to go into 2.5. This is a negative 5. Going to go in. It's just going in half of what its x coordinate is. I don't know of a better way to say that. Now, Vanessa and I were talking this morning. She was looking at this way. This is a length of 3 down here. So when you compress it, it'll be a length of 1.5. But I guess that's okay. But that's true. But I think it's almost better to grab some of those points and move them. And that's probably a better way to go. Okay. On the next one, we're just going to stretch it by 2, I think. So you stretch it by 2. Now you're looking at the y value. So this would be up here at 6. And this y value is still going to be at 0 because 2 times 0 is still 0. This y value is at negative 4. Is going to be down here at negative 8. Way down here. All these y values will be down here. This will still be at 0. This y value is at 2. It's now going to be at 4. So it's just going to look like right? It's just going to be twice. Again, just like sine graph and amplitude, this part's going to be twice as high this way, and this will go twice as much down this way. So it stretches in both directions from the y-axis. Okay? What's a negative on the outside do? Flips it. So this point right here is going to flip over to here. This point here is going to flip over. Oh, no, that's not right. It's going vertically, isn't it? Negative on the outside goes vertically. So this point here that's at 2 is going to be down here at -2. This point stays there. This point that's at -4 is going to be up at 4. That point will stay there. This point will go up to there. Oops, there. Missed it. Okay, this point that is at 3 is going to be down at -3. And so it's just going to flip like so. Okay. And then the other way would be flipping horizontally. So this point flips over to here, this point flips over to there, this point flips over to there, this point flips to there, and so forth and so on. This flips to there, this flips over to there, and so on. I missed it. Okay? So if you're doing that on the quiz, you're going to be careful and drawing a little bead over that. But, okay? And then don't forget that you could have some combinations of those things. And if you had a combination, I think you want to start on the inside. So if you had something like this, right? If you had something like this, you want to first compress it and then down through. Right? You compress it in like we did, and then you would go down through. Okay? Or shift this way first, and then maybe you're going to shift up and down. Okay? Kind of order of operations, basically. If you had a negative in front of there, right? Same thing. You compress it, flip it, down through. Press it horizontally, flip it vertically, shift down through. All right. Anything after that section? Any questions? Sam? 60. All right. 60 says that f of x equal x squared, and let g of x equal x squared plus 4x plus 3. Now, sometimes they give you a hint, almost makes it harder, because then you feel like you've got to do it that way. You wouldn't actually have to do it that way to solve this problem if this was on the quiz. They said you can complete the square. So let me go ahead and do it that way. Just to remind you what completing the square is. Completing the square is when you want to write something as a perfect square, right? And so like x plus 2 would be x squared plus 4x plus 4, right? Like that. Right? Now, how do we go backwards to that? Well, if you just take the first 2, if you take half of this, I don't know if you remember this from algebra class, but you take half of this as 2, you square it, that's how you get this last number for a perfect square. Take half of this and then square it. Why is that? Because when you do FOIL on this, you square this, then you do twice the inner product, so twice 2x. That's where the 4x, that's why you take half that, and then you square this. So half of that, square it, that's what you get. So we'd like there to be a 4 right here. Okay, half of that, square it. So what we can do is we go x squared plus 4x plus 4, and then minus 1. And so now that's the same thing. X squared plus 4x plus 4 minus 1 is the same as plus 3, right? And now we can take those first 3 and we can write it x plus 2 squared minus 1. So now what do you got? You got g of x equals, oh, well, what's that? That's just a plain x squared graph shifted 2 to the left and down 1, which is what they said. They said the g of x, that's the same as f of x plus 2 minus 1. X plus 2 plugged into this function, x plus 2 squared minus 1. Okay, so that's how you can do that with completing the square. I would say, I would probably, if I was working that problem, and I didn't want to complete the square, I wasn't sure how to do that, here's what I would do. If they're saying, okay, show that g of x is equal to f of x plus 2 minus 1, I would use what I call my German shorthand method. Remember that yesterday? If f of x is x squared, what's f of a? A squared, what's f of German short hair? German short hair squared, right? Now, what that means is, when you're doing f of anything, you take that anything and you plug it in, okay? So what I would do is I would look at this blue thing and I would think of that as my German short hair. So what does f of x plus 2 mean? It means take x plus 2 and plug it into the function, right? Plug it into the f function. So this means take this and stick it right there for that x, which means put it right there for that x, right? So the right side to me, when I look at this, I take that, there's my German short hair right there, okay? I'm going to take that and I'm going to plug it into there. So I'm going to get x plus 2 quantity squared minus 1, which is x squared plus 4x plus 4. So I guess what I'm saying is on the quiz, I wouldn't give you a hint like that, say complete the square. I would just ask, show that this is equal to this. And I would want you to be able to do that. I'd want you to be able to know that f of x plus 2 means plug in x plus 2 into it. Just like f of 7 means plug a 7 into it, right? So you plug that in and you simplify and you get x squared plus 4x plus 3. And you say, yeah, there it is. Got a math. Okay, that's how I would suggest doing it, as opposed to completing the square. But they both work. Okay. What else? So that'd be a tricky one, right? If we're talking about the quiz, there's some easier questions, there's some harder questions. You know, that would probably be on the tricky one. 55. Hemispheric water tank. Okay, so we've got, this is a little bit like that problem we did the other day, not quite the same. That had a cube. So we got this half a sphere. We got water in it to a certain level here. Okay, that's D right there. That's the depth. Okay, it's a 10-foot radius. Okay, so it says let V be the volume of the water and D is the depth. So what's V of 0? So this is what I was talking about the other day about in context, putting things in context. So what does V of 0 mean? It means what's the volume of the water when the depth is 0? So what's that? 0. Obviously there's no water. Okay? What is V of 10? That's asking what's the volume of the water when the depth is 10. Now when the depth is 10, this is going to be full, right? Because that's the radius is 10. So that'd be radius here. It's going to be full. Now, if this was a quiz, I would give you the formula for volume of the sphere. Maybe that's your question. 4/3 pi r cubed is the volume of the sphere, but this is only half, so 4/6, 2/3, right? 2/3, right? So that's the volume. So we put in 1,000, so that'd be 2,000, or put in a 10 cubes 1,000, so 2,000 pi over 3 would be your answer. So if you didn't know the volume of a sphere formula, then that would be problematic there. But I would give you the volume of the sphere. So V of 10 would be that number. Okay, just the volume of half a sphere. Yes.
Wouldn't you just have like 200, like your final equation be 200 divided by 3 times 5 times D, because sometimes your depth would be totally different.
Right, but that's...
But if the depth is...
No, because, well, see, now, if this is only partially full, now we got something totally different, because this is not a sphere.
Yeah.
You see what I mean?
Okay.
This piece right here is not, the sphere formula doesn't work, right? If it's full, it's 4/3 pi r cubed. If it's half full, it's 2/3 pi r cubed. But now, is it a fourth full? Just because it's, talk about this right here. If it's half full, that's half a sphere, okay? But if it's halfway up, if the depth is 5, is the bottom, is this thing half full, volume-wise? You get what I'm saying? If this is 10 here, and if we fill it up 5 deep, is that half of that? No, because there's less in this bottom half than there is up here, right? So we couldn't answer V of 5, in other words, right? That's why they didn't ask you what's V of 5, because that would take some other calculating, right? Well, it would take calculus, actually. It would take calculus we're going to learn later in the year, okay? But for right now, we could do a half a sphere with that geometric shape, or we can do it when it's empty. That's why I just asked you those two. Okay? All right. And then then which of those graphs could be V? A, B, C, or D? I think it's got to be C. It's got to start at 0, and that's just what we were talking about. The volume's going to be pretty small here originally. Remember, D is your depth. So you go up 1 foot. Was it feet? Is it feet? You go up 1 foot, and you got a little bit of volume. You go up another foot, you got a little more volume. You go up another foot. You remember we were talking about bigger chunks with the trapezoid the other day? Go up another foot, you get a bigger chunk of water, and then a bigger chunk and a bigger chunk of water. Every foot you go up, you're getting more and more water, right? And so all of a sudden that volume it's going to go up pretty slow, but then it's going to start getting faster as you pick up bigger and bigger chunks of water. Okay, so it would have to be C, not B. Not B. It's not linear. Okay. All right. Anything else? Anything else? Come on. I know there's other questions. Thank you. Okay. Now you might be the only one that's got a question 69, but I don't think so. So I'm glad you spoke up. This is an important type of question. This is about reading this graph. This is some examples of how we have to be able to read function notation in here. Okay, here's a g function. It says g of 1 is equal to 4. So here we go. So I'm going to plot that point. Okay, and it tells me g of 5 is equal to 2. All right, that's what I know about the g graph. That's all I know. Okay, and I know that it's concave up from 0 to 10. So what's that tell me that this has to do if it's concave up?
Concave down.
It's concave down? Where did I see concave up? Oh, it's 68. Oh, did I get the right points? They're the same points. Okay, good. Okay, so 68 and 69 are very similar. See, I should have assigned 68, and then there would have been tons of questions, right? But 69, the answer is in the back, so you feel okay. And maybe you looked at the back and said, oh, yeah, okay, and then you figured it out kind of in reverse. Fair enough. Could this graph go straight from that point to that point? No. It's got a curve, and so the graph's got to go where? Above or below that line? Concave up. It's concave down. Concave down. So it's got to go above that line, right? This graph the F graph's got to go above that line. Okay? And it may keep, going for a long time, whatever, but I don't know what it's doing for sure. It's not going to be flat there, but it's got the curve concave down, so it's got to be above that line. Okay. So, explain why g of 3, and this is that explaining stuff we talked about where you got to be able to put your thoughts into words. But sometimes a picture along with an explanation is okay. Why is g of 3 greater than 3? Somebody take a crack at it without just reading what was in the back. And maybe it wasn't even in the back. I don't even know. Sometimes they're not if you have to explain.
It's halfway between 1 and 5, so it can't directly be halfway.
Okay, I think you're on the right track. This is 1, this is 5. It's halfway in between at 3. Here's 3. Okay. Now, expand on that.
Like, so if you drew a straight line between the 2 points, that's what that would be. But it can't, since it's
okay, so all that stuff I kind of talked about in the setup is kind of what you're saying, right? So you would have had to, you may not have thought to connect those with a straight line, and you may not have put that together with concave down. So I kind of did some of the work there in the beginning, didn't I? And what Jason's saying is exactly right. He's using what I said to perfection, because that's where the 0.33 would be. If you look at this slope, what is it? It's down 1, 2, 3, and no, it's down 2 and over 4, so it's a slope of 1/2. So that means if you go down 1 you're going to go over 2, which is going to put you right there. So the point G of 3, 3 is right there on that line. And that's what you'd want to say. Now, I think a picture would be helpful to this explanation. I think it's very difficult to give a good explanation without that picture. Much easier to give an explanation with that picture. So you say, okay, G of 3 equals 3 would be right on a line between those 2 points. Since it's concave down, the curve has to go above the line, and so therefore the y value, remember, when you see G of 3, when you see this statement right here, you should be thinking y value, y value, y value, right? And so you would say the output, G of 3, has to be above, greater than 3. It's got to be above that line, and so that's why. Okay? Find a number L such that G of 4 is greater than L. How would you go about finding that? Jace, you want to tackle that part?
You can just use the line, and you know that's greater than you know what I'm saying?
Yes. So you tell me, what's that point at 4 on that line? What is it? Wouldn't it? 2.5, right? Because this is 2. My picture isn't very good. That's 2. This would be 2.5, 5 halves. So this would be the point. So G of 4 on that line, I'm not going to call it G of 4, but this would be 2.5 for a y value right here, right? That would be 2.5. But we want G of 4 to be greater than L, right? So you're saying G of, so I guess my question is, it says find a number L such that G of 4 is greater than L. Are you saying 2.5 would be that number? Would 2.5 be your answer for L? Because doesn't G of 4 have to be greater than 2.5? It does, right? It's got to be above that line. So G of 4 has to be greater than 2.5. Now, is there any other answer that would be acceptable? Wouldn't any number less, because you said greater than, so you were saying G of 4 has to be greater than 2.5. But, right? But the question is find the number L, right? So L could be 2.5. Right? Because G of 4 has to be greater than 2.5. But couldn't L be 2.4? Right? Doesn't G of 4 have to be greater than 2.4? Couldn't L be 0? Doesn't G of 4 have to be greater than 0? Now, I sense that some of you are saying, now wait a minute though, if you say G of 4 greater than 0, it could be 1, and that's not good enough, right? 1 is not G of 4, right? But we're not saying that if you pick 1 for L, that means any number greater than 1 is going to work here, right? That would just be saying G of 4 will be greater than 1, right? And there's no doubt that's true, right? Not only will G of 4 be greater than 1, it's going to be bigger than that. It's going to be greater than 2.5, okay? Think of it this way: if I had $100 in my pocket, and I said, and I was going to make you guess, and I said, well, the amount of money in my pocket is greater than 0. Isn't that a true statement? That's a true statement, right? The amount of money in my pocket is greater than 0. It's greater than 10. You know, it's even much greater than that. So it's a true statement to say that G of 4 is going to be greater than 1. That's a true statement. It's definitely going to be greater than 1. Matter of fact, it's got to be greater than 2.5. But it wouldn't be okay to say it's greater than 2.6. You couldn't go above 2.5. So, idea is any number, but the key, what Jay says, you got to find that number on that line, because concave down is going to be above it, concave up, the curve would have to go below. Okay? So that's kind of an important concept later on, but also reading that language and understanding what they're looking for is important too. Okay? All right, and that'll get easier as the year goes on. right? That's probably the hardest part of this quiz, and don't make it harder than it is, but some questions are tricky. This would definitely be one. Something like this would be tricky. Now, don't expect that there's going to be a question exactly like this on a quiz. You know, one of the things when you start a new class like calculus is figuring out what the quizzes are like, what the questions are like, you know, especially when you look at this assignment like this, right? I mean, it's a lot of kind of story problems, a lot of explaining, a lot of different types of things. So typically you can expect on a quiz that you're going to see many questions that will be similar to what you've done in homework, seem very similar. But there's also going to be questions, there are always going to be questions that probably stretch you and use the notation and the things we've talked about, but ask it in a different way and make you think about it. There's no question about it. So sometimes you get the feeling of, well, we didn't learn this, or we, you know, and what you're really thinking when you say we didn't learn this is you're thinking we didn't do a problem like this, right? And that's very true. You know, a lot of times it's true. We didn't do a problem like that. But if you put together the things that we have learned, and you really understand the concepts and the notation and the language, then you can answer them. Now, those are hard to study for. I get that, right? The best you can do is go through the homework, do the best you can, and ask questions when you understand. And that's why I was kind of saying, hey, come on, I know somebody's got to have a question about 69. It's not good enough to just look in the back, see the answer, kind of figure it out. If you're going through a bunch of questions and kind of going, okay, I kind of get it. I kind of get it. Then you're not being honest with yourself. You probably should come in and talk about it. You probably should ask and say, okay, I'm not quite sure what's going on with this. Okay? And have me try to explain it or work with somebody else or whatever, right? Because this class, more than probably any math class you've had, really tries to see, do you understand the concepts of what's going on? And can you apply it? Can you put it into a different type of problem? Okay? And there's going to be problems that are going to be very similar to the homework, no question. But there's also going to be those other kind too, okay? And so you've got to be honest with yourself as you go through here. Am I understanding what this is saying, or am I just getting the answer and willing to go on? Okay, so understand that. All right. Well, let's move on to just a couple things to talk about today. If you turn in your book to page 24. Basically, I'm going to do a quick run through of basic functions that we should really kind of know about. Now, it's not going to be totally necessary on this first quiz because I'm going to let you use your calculators for the most part. I think pretty much on the whole quiz. We're going to use, I think we're going to use calculators. Now, I'll let you know about that for sure more. So if you've got to graph a trig function or you've got to graph, I think there was one in the homework, nobody asked about it, but number, it was about even odd. What number was that? 7 actually is the one I was thinking about. Yeah, 7 I was thinking about. 63 talked about even odd a little bit. 7 is the one I was thinking about where they give you this function. Now that would actually be a cubic function. We're going to talk about that one. Matter of fact, we can talk about that one here in a minute. It was, what was it, t plus 1 and t minus 2 squared. Okay, that was, what did they call that, g. Okay. If you were given a function like that and asked about even, odd, whatever, you could graph it. Okay, so you could graph it on your calculator. Maybe that's what you did on this one. And then see if it has that symmetry of, you know, and so forth. Okay? So it's not like you're going to have this memorized, but we're not going to really go through and review it again. Whenever it comes up, we'll review these different things. But it's one of those things that the more you know and the more comfortable you are with what these functions are like, the better off you're going to be, especially in a no calculator situation. So going forward, as much of this as you can remember, the better. And the more we run into it, the better you'll get at it. So first type of function I want to talk about is polynomial functions. Okay, so this is where, remember in that reading I had you do in the prerequisites, it talked about different families of functions you had to know about. Some of you talked about exponential and log being an issue, piecewise defined. Well, we already talked about piecewise. So a polynomial function is any kind of function that has here'd be a cubic, for example. But any kind of function that just has integer, or not even integer, whole number exponents. So x to the first, x to the second, x to the third, x to the fourth, no fractional powers, none of that. Okay, those are polynomials, okay? Now, there's linear, which is, of course, your x to the first type of function, okay? There's quadratic, which is when you get into your x squareds, right? I mean, that's like your y equals x stuff. This is like your y equals x squared, right? And those always make parabolas, right? There's your cubics, right? Which is your x cubed type of functions. And cubics can look like that. We're going to address that here in a minute, okay? And so what you start to notice is, well, if I do a fourth degree, those are actually called quartic. A quartic, if it's x to the fourth, now not all of them look exactly like this, but you could get a W, kind of a W shape. Okay, now it's possible that a fourth degree, if you graph plain old x to the fourth, it would look like a parabola. Okay, it would look like a parabola. So, okay, it wouldn't have to look kind of like a W shape. Plain old x to the fourth is just going to look like a U shape. Okay, but it could look like that. Okay. And so forth and so on. And what you start to recognize is that odd powers, if you have odd powers like x to the first, x to the third, those tails are going to go opposite directions, right? Tails are going to go opposite. If you have even functions, tails are going to go the same way, either up or down, okay? That kind of a thing. If you put a negative on the leading coefficient, it's going to flip it. If you put a negative x squared, we all know that parabola will go upside down. Same thing, if you put a negative in front of an x to the fourth, that's going to flip it, and those tails will go down. If you put a negative in front of this, it'll flip and go the other way. So instead of down to up, it'll go the other way. So it'll flip around on a cubic. Okay, those are just some things to know. Polynomial functions, the domain is all reals. You never run into any problems plugging into a polynomial. The domain is always all reals. You could get even at odd functions. A basic x cubed is odd, a basic x squared is even, but they wouldn't have to be if you shifted them and so forth. Okay, so those are basically polynomial. That's what's going to happen with polynomial functions. Now, also, and we talk about degree. So if we talk about a degree 5 polynomial, what's that mean? Well, it means it's x to the 5th, right? Degree 5 means it's like x to the 5th. So it could be x to the 5th plus 4x to the 4th minus 2x cubed, whatever. But its highest power is going to be 5. Now, that means that it has at most 5 solutions. If you're going to do an x to the 5th plus 3x to the 4th, equals 0, that is what you're talking about. If you take a polynomial and set it equal to 0, it means it will have at most 5 solutions, but it might have fewer. Just like a quadratic could have 2 solutions, but it might just have 1 and it might have no solution, right? And the reason it has 5 is it could cross as many as 5 times if it's x to the 5th, right? Now that would actually be a negative. That would be a negative if it started, the tails are going a different way. Instead of starting down here and going up like that, like it normally would, it goes from here and there. But a 5th degree can have at most 4 humps. At most. Now it might not. You might have a 5th degree that just does this. Might not have any humps, right? It could just do that, okay? It's possible. But it could have at most 4 humps, and it could cross the x-axis at most 5 times, right? And so that's where Harish is getting the idea that this could have 5 solutions, right? Where does this equal 0? Well, that'd be everywhere its y is 0, everywhere it crosses the x-axis. Well, that could be 5 times, but you know what? That could be shifted up. Whoops. That could be shifted up to where it would have how many? It still has 4 humps, right? But it only crosses the x-axis 1 time. I mean, it's possible that it just has 1 solution, okay? If you remember from Algebra 2, that would mean the other 4 are complex. Those are imaginary numbers. We're not going to get into that. So we'll just talk about this. So it's possible it just has one solution, or 2, or 3, or something like that. So you're going to have some questions in the homework today where it asks you about that, where it says, how many times is q of x equal 0, or can q of x equal, when is q of x positive, or, different things like that, just asking about polynomials with different degrees, okay? So again, if you have an odd degree, the tails are going to go opposite. If you have a degree 6, right, now that means it could have as many as 5 humps, always one fewer, but that's the most it could have, but it also might just look like a parabola too, right? So it might just have 1 hump, it might have 3 humps, it might have 5 humps. It'll have at most 1 fewer than the degree. And if the x-axis ran right through here, right, how many times would it equal 0? 1, 2, 3, 4, 5, 6. It could have at most 6 solutions. If you took a degree 6 equation and set it equal to 0 and wanted to solve it, you could have up to 6 solutions. Okay? All right. That's polynomial functions. They're nice. We work with them a lot because in calculus we talked about concave up and concave down. Those give us a lot of nice concavity. They give us a lot of inflection points, where the concavity changes. We get a lot of local max, local min stuff with polynomials, so we can do a lot of good calculus stuff, and they're nice and easy to work with, right? They don't have any too much crazy stuff going on. Okay, so that's polynomials. Okay, let's move on. Let's talk about exponential functions here real quick. Exponential functions always cross at the point 0, 1, right? We talked about that yesterday. 2 to the x, e to the x, 4 to the x. Now, remember, e is approximately 2.718, okay? That's what e is approximately as a number, okay? So 2 to the x is not quite as steep. E to the x is right in here. 4 to the x would be a little steeper, so the bigger that base is, the steeper it is, okay? Notice if you have exponential decay, like this one, that goes the other way. Now, that can also be written 2 to the negative x, right? 2 to the negative x, a negative power is what you usually see with exponential decay. You see it written as a negative power. But remember, 2 to the negative x could be written 2 to the negative 1 to the x, right? Power and power you multiply, which is 1/2 to the x. So that's how they write it. So if you have a base less than 1, a fraction, that is between 0 and 1, raised to the x, you got exponential decay. But it still crosses at the point 0, 1. Okay? So that's exponential functions. The domain on those would always be all reals, right? You can plug in anything into your power here that you want. Okay? The range, unless it's been shifted, the range would just be positives. You're always going to get positives out of that, right? You take a positive base and you raise it to anything, you're always going to get a positive value. Okay? If you raise it to a negative, you get the reciprocal. That's why it goes up over here. Okay. So forth. Okay, so that's exponential functions. Pretty basic looking thing there. Logs are the inverse of those, right? The reflection. So if you take, if this was e to the x here, we're going to talk about inverse functions later, but that would be the inverse under reflecting here in this line. This log base e, this is ln x right here. This is ln x log base e. So that is the mirror. Those two are mirror images there. Okay, so logs and exponentials are mirror functions, mirror images of each other. Okay, but here's the different logs. So again, same thing. If you had a base half, we hardly ever run into something like that. The one you mainly want to know is natural log, but it crosses at 1, 0, right? We interchange the x and the y. So exponentials cross at 0, 1. Logs cross at 1, 0. It's one of the graphs I will constantly be reminding you out throughout the year, and I don't know why it continues to be hard, but that is the log graph. So whenever you have ln x, right, we have that. Okay. Now, why is it important to know about the log graph? Let's combine the log graph with what we did yesterday. So here's what happens. Uh-oh. All right, here's what happens. You do a bunch of calculus, and you to answer the calculus question, we don't know that yet, the calculus part, but basically to answer the question about the calculus, we have to look at this graph right here. And we have to figure out when is this less than 0? Or that'd be like saying, when is that negative, right? We'd have to know when is ln x minus 2 negative, and this is no calculus. So we'd have to find an interval to answer this question. So we do some calculus, we get down to here. To answer the question about the calculus, we need to know when is natural log x minus 2 negative. Okay, well, if you know what the graph looks like, this is a piece of cake. We know the basic graph goes through here. It comes up, this is a vertical asymptote, and it doesn't level off, but it gets almost level. And this is a vertical asymptote here. If you just memorize this graph. Now, what does the x minus 2 do? Shifts it to the right 2. So that means it's going to cross here. And then where's its vertical asymptote going to be? Right here, right? Because that's got to shift over 2. And so this graph's going to come down and be like this. So when is this graph negative? When I say the graph, I'm talking about the outputs. When are the outputs negative? Between where and where? Between 2 and 3. That's an interval now, not an ordered pair. That's an interval, right? So the answer to the question is between 2 and 3. Between 2 and 3. And I knew that because I knew what the log graph looks like. I knew that if I shift it over 2 to the right, it's going to look like this. And that graph is negative or below the x-axis between 2 and 3. So knowing the log graph is about the only way to answer that question. Otherwise, trying to answer that is very difficult. But if you just know the basic log graph looks like, and then you shift it over 2, now you're in business. Okay, that's one example that I can think of where we need to know what the basic log graph looks like. Okay, all right, moving on. So we talked about logs a little bit. You're going to get into those a little more. Okay, the domain on a log graph, domain is positive, right? X has to be positive. You can't put in a negative into a log. You can't do log of a negative, right? Doesn't make sense. Log, you want to do log of positive values. Okay. All right, and then the trig stuff. Okay, and we've already went over some trig unit circle stuff. I wouldn't put that in my notes necessarily. We already talked about this. I want to show you something else here. You might have saw this last year. So here's a unit circle. So here's like 30 degrees. Here's pi 6. Now I want to, one more time, I want to clarify something on the unit circle. Why do we use the unit circle? Why do we want to use something where the radius is 1? Why is that helpful? Think SOHCAHTOA. Think SOHCAHTOA. What does that mean in SOHCAHTOA? Sine is opposite over hypotenuse, right? So the sine of pi 6, or 30 degrees, has to be the opposite, which is our y value, over the hypotenuse. Well, if the hypotenuse is 1, then the sine value is just what? The opposite, right? Which is the y value, right? That's why I was saying with unit circle there, sine is y, sine is y, sine is y. How come? Because we're using the unit circle. Because we're using the unit circle, we can ignore the hypotenuse. So we just have, so the sine is y. And what's cosine? It's adjacent over hypotenuse, right? And the cosine is, so that would be x over 1, right? And so since the 1 doesn't matter then, the cosine is x. The cosine is x. That's why we use the unit circle. Okay? So we can just say, all right, there's the cosine and there's the sine. Those coordinates on the unit circle. All right? All right. And then the radians, the reason we use radians is this blue number right here, or this blue value. It's the arc length. Right? That's 30 degrees is the angle, the rotation, but pi 6 is the arc length. Because what's the circumference of a circle? 2 pi r. But what's r in the unit circle? It's 1. So what's 2 pi times 1? 2 pi. So this distance is 2 pi. That's why radian, that's why 2 pi is 360. That's why pi is 180. It's length, it's circumference, right? So in the unit circle, pi, when we say sine of pi 6, we're talking about this length. When we say 30 degrees, we're talking about a rotation, right? We talk about pi 6, it's this length, but that's only true in the unit circle, right? If this radius was 2, then all the way around would be 4 pi, right? And then everything would be messed up. So in the unit circle, the arc length is 2 pi, right, around the circle. That's why we use it. Okay, just to review those things. All right. Because pi 6, we always think that's 30. We think pi is 180, but also pi is just 3.14, right? Pi is 3.14. So in the unit circle, this is about 3.14 divided by 6. This arc length is about a half of a unit, right? It's 6.28 all the way around. So another thing I think is useful to know about the unit circle is that this is about 1.57, this is 3.14, this is 4.72, and this is 6.28. That's 2 pi. 2 pi is 6.28. So yeah, we think 360 degrees, but as far as a length, right, that's what radians really are. So pi 6, which is about 0.5 to there, another 0.5 to there, and another 0.5 to there, that's how we get about 1.57. That's pi divided by 2. 3.14 divided by 2. Okay? So these numbers, that's what radian numbers actually look like, okay, when we go around the circle. All right. So, but we already talked about these values, and knowing those trig values would be good to know. You know, you're not going to have to know them for this quiz, right? But we got a quiz coming up here. Maybe not the next one, but the one after that, where we're going to have to know them. So practicing with those, and we're going to do some trig stuff tomorrow. Actually, some more trig stuff tomorrow. So we'll get into that a little bit. Okay. And of course the sine graph then, and I think maybe you saw this last year, but if I move around the circle here, okay, so this is my arc length. Here's 3.14, see right there. Here's 4.71 right now. There's 4.7 or 4.72, and now we're coming around and there's 6.28 right there. Okay, so this length here is my radians, and on a graph, those are going to be along the x-axis, okay? Now, if I want to show sine, sine is the y. So that blue line is the y, okay? So what do we get? See how it's getting bigger, 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 bigger? Now it's 1, now it's getting littler, 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 and now it's down at 0, and now it's negative and getting bigger, 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 negative, and now it's getting -1, and now it's getting littler. That's why the sine graph looks like it does, because sine is the y value, okay? So if we hide that, now we look at the x value, okay? What's the x value do? Okay, it's -1, but now it's getting smaller, smaller, smaller. Now it's 0. Now it's getting bigger, bigger, bigger. Now it's 1. So at the beginning, the x value is 1, and then it gets smaller, and that's why the cosine starts up there at 1, right? So radian is the input. That's the red. The x coordinate is the cosine. So that's where the graphs look like they do, okay? And they repeat, and that's why they repeat every 2 pi, because once it wraps around here, it goes again. Okay? All right. So, just again, a little bit more on the trig functions. We're not going to talk too much about tangent and those. They do give you the graphs on page 32. If you turn to page 32, they do show you the tangent graph. I want to give you some work time here, so I don't want to go into it too much, but the tangent graph, we can look at it here on here real quick. Okay, so the tangent graph, if we start, okay, oops. So we start here. Tangent's actually the slope. Tangent's actually the slope of this line. Okay, right? Because what's SOHCAHTOA? What's tangent? Opposite over adjacent. Well, you know what that is? That's y over x. That's rise over run. Okay, tangent is y over x. So tangent's the slope of this line. So it starts out 0 right now. Okay, now it's a 0 slope. Now it's a negative slope. But now what happens on a vertical line? It's a slope. Infinite, right? Undefined, vertical. So that's why you get those vertical asymptotes. Okay, so you get the vertical asymptotes at pi halves and at 3 pi halves, because that's when the slope of your line here would be undefined. Okay? All right. So, homework 1.3, Okay, 1.3 homework. So this is, again, these questions could be on the question about domain and range and these different types of functions. These are what we call our elementary functions, our basic functions that everything else is built off of. Okay, and so knowing about them is important. But on a quiz where you have the calculator, if you can put it in and graph it, that helps a lot. That can help you see domain and range and even, odd, periodic, that kind of stuff. Okay, but I would suggest when you're doing this homework to try to do as much of it without a calculator. A lot of the questions aren't going to do you any good with a calculator anyway, because they're not going to give you an equation. They're just going to give you they're going to say it's a degree 6 or it's an exponential, whatever thing. But if it calls for a calculator, if you think that's helpful, go ahead and use it.